So thank you, and my name is Qing, and I'm a PhD student here at ETH Zurich. And today I'm going to talk about domain adaptation for data-driven fault diagnosis. So data-driven methods have been successfully applied on a large range of general tasks. For example, on the image classification task, we have known that data-driven methods have been outperforming human performance for several years. And for example, on machine translation, data-driven methods have enabled us to use our own phone to do machine translation. And also, they enable us to do detection and segmentation in a even more dynamic environment. And with the help of data-driven methods, we are even able to help the doctors to diagnose eye diseases. And all of those sounds promising, but how about their performance on industry applications? Well, we've heard some successful stories. For example, in DeepMind, they reduced the Google data center's cooling bill by 40%. And Fujitsu reduces development time of parts assembly machines by 80% while maintaining a high recognition rate. And all of these sounds exciting, but the real question is, are data-driven methods really ready for a wider range of industry applications? And we actually found some potential problem. For example, the data-driven methods are usually in data-hungry models, which means that unlike human beings, which requires only a few examples to learn a new concept, data-driven methods usually require a huge amount of label data to get it trained. Let's take a look at the popular ResNet 50 as an example. So here we have the ResNet 50 in architecture, and it roughly contains 25 million of parameters. And to train such a large amount of parameters, you need an even more amount of data points and label data points to make it work. And when you don't have such a large amount of label data, then the network may, or most likely will overfit to the given training data set. And in this case, the representativeness of your training set matters a lot. But in reality, we know that in industry applications, labeled data are actually rare, and sometimes we don't even have access to a huge amount of label data. So what will happen if the training data sets are not representative? Well, most likely, the performance is going to suffer a significant drop. So here we have an example from image classification. So on the left side, we have the data set from Amazon, and the task is quite similar, just classify different objects. And if you train an SVM on it, then we get an okayish accuracy around 50%. But if you try to directly use this model and use it on a similar but slightly different data set called webcam, which is the same objects taken by a webcam. And in this case, the performance is already going to suffer a lot. And as you can see that because their training data set is not representative for their target data, the trained model of the SVM is going to, performance of it is going to decrease a lot. And similar stories can be seen in lots of cases. And for example, if you train a model for, if you train a maintenance model for one specific type of engine, and if you try to directly use it for the target domain, which is a new model, then most likely the model will fail. And this is because the training data is no longer representative for the target domain. And the problem is actually more severe for fault diagnosis in the wild. And very often we have a source machine which is well-studied, which is also well-labeled because we have some engineers studying for several years. And then finally we train a model out of it. But then suddenly one day the company has a new target machine and it's newly set up and probably it's not yet labeled and probably we don't even have lots of data points out of it. And most likely it's going to running in a different operating conditions and probably some components of it are non-identical comparing to the previous source machine. So in this case, the source data cannot represent the target machines well because the target machine is running in a different operating condition because their components are non-identical. So in this case, the model we train from source machine is more likely to suffer a performance deterioration for the target machine. And this phenomenon is often called a domain shift, which means that the target domain is different from the source domain. And we can better visualize this in a toy example. So on the left side, we have a source domain, and we have this as a toy example. We have two different colors of points. We have blue points, we have yellow points. And since it's a very simple example, we can just directly draw a straight line as a source classifier. And in this case, when we try to directly use perfect source classifier and directly apply it to the target data, which suffers a rotation shift from the source domain, as you can see that quite a few examples get misclassified. And this is because of the source domain and data is no longer representative for the target domain, and this is called the domain shift. So now that we know very often there are domain shifts when we have a source data and we have a target domain, so how should we deal with it? Actually, there's a quite powerful tool called Domain-Adaptation that has a promising perspective for this. So in a domain adaptation setup, we again have the labeled source domain with everything perfect. But in addition, we have the unlabeled target domain data, which help us to learn how the data distribution of the target data is going to look like. And the idea of domain adaptation is that we can try to align the source data and target data to align the distributions. And eventually, we can learn an adapted domain, and we can have an adaptive classifier, which can perform better in our target domain. And from a distribution perspective view, we can better visualize this in this example here. So assume that we have the source domain in purple, and we have the target domain in gray. And we try to, the idea of domain adaptation is that we try to align them together, which means that we try to make them overlap as much as possible. So in this case, if we use a supervision from the source domain and we train a classifier, the classifier can also be used in our target domain. So now comes the question, how can we achieve this adaptation and knowing that we can make use of the unlabeled data from the target machine? So let's start the journey from a very basic neural network. So here on the left side, we have a feature extractor and we have a classifier. And the two components can do fault diagnosis for some specific signals. So the question is, how should we add domain adaptation ability to this network? So one intuition is that since now we know that the input signals and from the source and the input signals from the target actually have different distributions, so we can try to align the distributions in intermediate layers. And following this intuition, we can quickly have this AdaBN method, which tries to do layer-wise adaptation by matching the statistics. And probably you've already heard of batch normalizations. And batch normalizations just given the input, batch normalization layers try to normalize signals into a unit Gaussian distribution. And AdaBN is nothing more but trying to keep different batch normalization statistics for source and target, so that the source signals are aligned to a unit Gaussian distribution, and the target signals are also aligned to a unit Gaussian distribution. And in this way, the two distributions align quite well. And the advantage of this method is that the approach is simple and elegant, and the disadvantage is that the performance is actually not optimized because we're only doing this in the forward passing loop. And so now we know that AdaBN can adapt via matching statistics. The question is, can we adapt between domains via backpropagation? Because we know that backpropagations are a quite powerful tool. And the answer is yes, we can actually explicitly model the source and target discrepancy. And so here we have the off-the-shelf solution called maximum mean discrepancy, which is called MMD. So basically the idea is that you take the source features and the target features, and then you apply a transformation, and then the kernel trick, and then you measure distance in the embedding space, and then you use this distance to estimate the discrepancy between the source and target domain. And given this powerful tool, we can immediately come up with a maximum mean discrepancy minimization approach, which tries to use the MMD as an additional loss to minimize. So here we again have the source features extractor, the classifier, and the target feature extractor. So both the feature extractors are actually shared. And after we feed the data, we get the source features, and then we get the target features. So basically, the MMD calculates the discrepancy between the source features and the target features. And we directly minimize this discrepancy. And by minimizing it, we are forcing the source features to look like target features. And in this way, if we have a source classifier, it can be also applied, or it can also have a good performance on the target data. And this approach provides a finer alignment comparing to AdaBN. But the disadvantage of it is that the model complexity is quadratic. And very often, if you want to have a fine estimation of the discrepancy, you have to apply multiple kernels, which even makes it more complex. So explicit discrepancy modeling by MMD is quite expensive. And are there any alternative, cheaper solutions? Well, there actually is the solution called adversarial training. And you probably already heard of it via Twitter or online sources. You've probably already seen these generated faces online. And the idea behind the adversarial alignment is actually quite similar to these GANs. So in a GAN, you usually have a forger which tries to generate a similar or realistic data, and we also have a detective which tries to tell the difference between the real data and the forged data. So how do we incorporate this idea into our framework? So here we have the domain-adversarial training, and we again have our feature extractor and our classifier. And same as before, we just minimize the classification loss. But additionally, we have the discriminator, which is simply actually a two-class classifier. And the discriminator acts as a detective, which tries to tell the difference between source features and target features. And we, of course, want to have a good detective, which means that we minimize discrepancy loss with regard to the discriminator weights, so that the detective is a good performing detective. And additionally, we are encouraging the forger, the feature extractor, to fool the discriminator and generate unbiased features. This means that we are asking the feature extractor to generate source features and target features that are difficult for the discriminator to tell where the source is. And this is achieved by maximizing the discriminator loss and the detective loss with regard to the feature extractor weights. And you can see that this includes a minimax game, which includes an adversarial training between a forger and a detective. And so this is where the name adversarial training comes from. So actually, the minimax game can be easily implemented using a gradient reverse layer and can be trained in an end-to-end fashion. And this adversarial alignment has been proved to be able to implicitly reduce the edge divergence between source and target distributions. And the good news is that by doing so, the complexity of the whole model is actually linear instead of quadratic. So we save quite a lot of time. So now that we have all these tools of domain adaptation, let's have a quick case study on the CWRU, the Case Western Reserve University Berry dataset. So this dataset is a Berry dataset, and it contains 10 different classes. And so we have the first class as a healthy class, and the rest 9 as 9 different faults. And what we do is that we try to do a domain adaptation between different operating conditions. So assume that we have the label data for one source domain, and we try to directly adapt it to a new operating condition. And in this case, we are adapting between different loads. So we compare the performance of the previous mentioned methods on the CWRU dataset, and we try to do a fair comparison, meaning that we use the same basic architecture, we use the same budget for tuning, and we use the same optimizer and same learning rates. So here we have the results of the average accuracy. As you can see that the simple solution of adaptive batch normalization is already giving us quite a lot of improvement comparing to the baseline. And with the explicitly modeling of the discrepancy between source and target, we are having even much better performance. And finally, the described adversarial training method can also have a very fine alignment of their distributions. And regarding the model efficiency, as we mentioned before, and the MMD method is an explicit modeling method and is quadratic with regard to the training sample, so it takes much longer time for training. And the adversarial method and takes a few less time. And the AdaBN method is actually quite quick because it doesn't require much more computational burden. So let's have a quick summary of what we have described before. So we have described some domain adaptation methods, and all of them are managed to improve the model performance. And the adversarial method provided provided competitive results using significantly less training time. And we can also see that AdaBN is a simple and elegant solution, which is fast, but performs worse than the other two. So let's come back to the initial scenario we are considering. So we have a source machine, and we have a newly set up target machine, and it's running under different operating conditions. Have we really solved this problem already? But the answer is actually not really, because until now, we assume that we have full access to the target faults. But we know that actually in reality, most of the time, the machine is running in a healthy mode, and some faults are really rare. And especially when it comes to a newly set up machine, some faults are not possible to collect in the beginning of their lifespan. So this leads us to the second part of the presentation, which we call it a missing class aware adaptation. So this was inspired by the fact that most faults are actually rare. And in this case, we are considering the fact that in the target training data, we actually don't really have access to some of the faults. And probably we have fault 1 and fault 2, but probably most likely we are not going to have access to the rest of the faults. But as a fault diagnosis model, we still want to evaluate it on all sorts of faults. So how should we deal with this issue? Well, a naive approach would directly align using the previous methods and directly align the complete source domain with the partial target domain together using the previous methods. But this is actually quite wrong because you're aligning a large source domain with a small target domain. And this misalignment can be demonstrated in a toy example. Here we show a toy example using the source as the black and white digits and the target as their colorful background MNIST dataset. So if we train a model using the Domain-Adversarial method and we visualize the features, you'll see that part of the target features are actually aligned with the complete source data. And this is this is not good alignment because we should see red actually overlap with blue on all different classes instead of this partial alignment. And the wrong alignment due to the missing classes can be better visualized in a figure here. So here we have on the x-axis the number of missing classes in target training data, and we have their accuracy and on the y-axis. As you can see that with a growing number of missing classes and the domain adaptation method, actually the performance of it drops significantly. And when there are more than 8 different classes, the performance actually is worse than the source-only baseline, which doesn't have access to any target data. So we know that discriminability is actually hurt because of misalignment. So how can we preserve discriminability, which we learned from the source domain? So we propose a method called unilateral alignment, comparing to the previous method we call bilateral. So recall that in most domain adaptation methods, we are trying to align the source domain with the target domain, and we're actually moving both source and target to something intermediate. And when it comes to missing classes, during this process, the interclass relationship between the classes in source is messed up. But we need this discriminability from the source domain. So what we propose here is that we keep the source features there and without hurting the discriminability, and we try to align the target domain to the source domain instead of doing it bilaterally. So how is it achieved? So in stage 1, we train a standard feature extractor, the standard classifier, and we get the pre-trained features. And in this way, we learn the discriminability from the source domain. And in stage 2, we make use of this additional information from the source domain as the pre-trained features. And we calculate the distance between the pre-trained features and the new source features. And we calculate the distance and minimize this consistency loss. So in this way, we preserve the source features, and we try to align the target features to the source features. So in the final stage, the loss contains 3 parts: the usual classification loss, the discriminator loss, and additionally, our consistency loss. And this performs the simple consistency unilateral alignment addition and has actually helped us a lot in combating the missing class phenomenon. So here we have the red line as our baseline adversarial training method. And with our additional unilateral consistency loss, we actually avoid the model collapsing when there are more missing classes. So we now prove that we have achieved better alignment in case of missing faults, and we are one step closer to domain adaptation for fault diagnosis in the wild. But we are still facing lots of further small troubles or further obstacles in the way for domain adaptation for fault diagnosis in the wild. For example, we are still facing imbalanced data. We are facing continuous domains because previously we only described a discrete domain case. And we are also going to encounter heterogeneous input. But we have demonstrated the domain adaptation is actually a promising direction, which can save the labeling faults. We can also save the effort on collecting the data. So we demonstrated in the first example that we can adapt from one operating condition to the other. And we have shown that we can also, we believe that it is also possible to do adaptation from one machine to a fleet. And we believe that it is also possible to do adaptation from one manufacturer to another. So the take-home message is that we believe that domain adaptation is almost ready for real-life industry applications. Thank you for attention.
Oh, do you have an actual audience there that was clapping, Shin?
Yes, with the team here.
Oh, I feel you're very lucky as opposed to those of us.
Yeah. I'm the luckiest presenter today.
Okay. Okay, excellent presentation. And actually, lots of questions were generated from your presentation on the Slido app. And so I want to get time for one, but let me say to everyone listening, keep sending in the questions because we have we're going to keep on schedule, but we're going to have a half-hour discussion session later. So keep sending in the questions. And also, if you see someone else's question and you like it, you have the ability to give it kind of a thumbs up that you like it, and then we can ask them in prioritized order. I'll just ask, we just have 1 minute before the next speaker, but the first one I see here is, Shin, did you try setups in which source and target data were more different? For example, different bearing types.
So in our current setup, we are actually only adapting between different loads. But of course, there are similar loads and different loads. And we do see that when the load difference is large, the domain discrepancy is larger. And we are now currently doing some research on trying to learn from different sensor locations as an adaptation. And we believe that it is really a good direction also to try to adapt between different bearing types. And it's a good future direction. Thanks for the question.
Okay, thank you very much.